Thanks, Niranjana, for the introduction and for the invitation to be here today. I'm very happy to present some of my recent work with all of you, and welcome to my talk. Um, so, the major theme of today's talk is going to be non-Euclidean data. And just to get into the groove of things, um, how data used to look in the past is mostly in the form of numbers that could be organized as the rows of a data table. And we are very used to seeing that situation. But increasingly often, it's getting more and more common to find data which do not have this form. For example, here, we have a situation where a modern data scientist might come across data where each data point itself is a random curve. One could also have situations where each data point is a random network. So as you can see, this is a situation in the past which has evolved to more complex situations now, but there is something common in between all these three situations. And may I ask what's common?
You can analyze it manifold.
Okay, that's a good answer, but suppose something is not in a manifold, but still might be having some kind of similarities between the data objects. So the common part of all these three things is that given any two data point, you might be able to compute how far apart they are in an abstract space. So there is a concept of distance or metric that gives you how far apart the data points are. And that is the situation which is common in between all these three plots that I presented in this slide. Okay, just to set up the notations, non-Euclidean data, also known as random objects, are essentially metric space valued random variables. So here, omega d is a separable metric space where omega is the space and d is the metric, and b omega is the Borel sigma algebra on omega, and x1 to xn are IID omega valued random variables. And here on, I'm going to refer to them as random objects. And I'll assume that they are generated according to some law P, which is a law on the metric space itself. And a special case that we see all the time is when omega is the space RD and D is the Euclidean metric. But non-Euclidean statistics goes beyond that, and quite commonly one comes across distributional data where the data point themselves are univariate distributions. And one could work with different kinds of metric on the space of distributions. And what you see here is just one possibility, which is the two Wasserstein metric, which is just the L2 distance between their quantile representations. It's quite common to come across matrix valued data in the form of, I don't know what happened. Okay. Okay, let me actually. Yeah, I think I clicked on something that brought me to the very last page of my talk. Okay, I think I was here. Yeah, so matrix value data where, again, there are many possibilities of metrics. And here is the Frobenius metric between two matrices. Compositional data are data where each vector is a bunch of compositions. So they have non-negative entries that sum up to 1. In general, they are housed in a simplex. And there are various choice of metrics that you can adopt in that space. And one possibility is that you took their square root transformation and embed them on a sphere, and then look at the geodesic distance between them on the sphere. Again, these are some specific examples and only a few choices of metric, and these are not the one, these are the ones where our method applies, but it's not just limited to these. There are many, many other situations where we can go. So again, what kind of tools are we avoiding to adopt? Because when you're in a metric space, addition, subtraction, and scalar multiplications are operations that do not work. For example, you cannot take two random distributions and just subtract them and get anything meaningful. Canonical ordering is something you don't have even in RD. Like there are various notions, some proposals of how to order them, but there is not a unanimous ordering that you can get. But with distances, one could always figure out how far apart 2 points are, and that is going to be the only tool that we are going to adopt for the problem that I'm going to talk about today. Okay. So the problem that we are going to focus on is independence testing in this modern data framework, and it comes up in various situations. For example, in medical research, one might often be interested to see if brain functional connectivity networks are independent of the gut microbiome compositions, for example. In market research, you might be interested to see if customer purchasing distributions are independent of their social networks. In ecology, are species distributions independent of forest coverage? And more recently, uh, you can use independence testing to segment watermark text from language models. So these are the various situations where independence testing is very relevant in this day. And just to give you some flavor, I have three situations here where we have paired data where the first element are networks and the second, so first element are random distributions and the second are networks. And in one out of these three situations, the distributions are not independent of the networks, but in two others, they are independent. And I'm going to take a poll to see how many of you feel, how many of you can identify which is the correct one. So how many of you think it's number one where the distributions are dependent on the networks? Number two? Okay. 3.5 hands. Number three? Okay, if I have to insist and ask you to pick one. So let's say 1, 2, or 3. So how many hands for 1? Okay, and 2? Okay, and 3? Yeah, at this point, it's like a psychological game. It's like you're thinking what I'm not thinking, and then I'm thinking what you're not thinking in this way, but I'm not going to disclose the answer now. We are going to come back to it in a few slides. Okay, so just to give you a small outline of today's talk, first I'm going to introduce distance profiles that characterize data distributions in metric spaces. And then I'll present an independence testing framework for random objects, which is powerful against all alternatives. And then I'll discuss related works and compare with the state of the art. And finally, I'll talk about some future extensions. Okay, distance profiles. These are very simple things. The distance profile of a point omega in your big space omega is just the distribution of distances around omega as dictated by the data. So you can imagine it is from the how we estimate it, it is the proportion of data points included in balls of increasing radius around omega. So that is the distance profile of omega. It's just how the distances around omega are distributed given the data distribution. So just a toy example. Here is just a very simple example that we all can identify with, just the bivariate normal distribution. And I've taken 4 points, which are our potential candidates for omega. So here is 0, 0, and then 2, 0, 4, 0, and 2, 2. Now, if you look at the distance profile of 0, 0, you can see that more mass is on smaller numbers. Because imagine the bivariate normal distribution. If you're at the point 0, 0, that's when the distances are more frequently smaller than if you are somewhere out on the periphery of your data cloud. Then 2, 0 is here, 4, 0 is here, and 2, 2 is here. So the idea is that the more central you are, the distance profiles will load more on smaller distances. And as you go further out, the distance profiles will shift to the right, like it will have more and more weight on larger distances. And of course, this is a very simplistic situation where I'm talking about a bivariate normal distribution. But in similar situation, the more central you are, the smaller distances will get more weights. But of course, this can be very erratic, like in real world where distances could be all over the place. But just to give some situation where we can see what these objects are, it will at least have this very nice pattern when we have something symmetric and with a mode and so on. Now, the question is, can these distance profiles be useful for statistical analysis? And something that I'll ask here is more ambitious. Can the collection of distance profiles actually characterize your underlying distribution P? So just a reminder, P is a probability measure on your metric space omega. Yes.
Explain once again what you mean by points in the center or the beginning.
Oh yeah. Sure. So just imagine the bivariate normal distribution. A point in the center, say 0, 0, right? That's the central point if the mean is 0. And if you look at the distribution of distances around 0, 0, then the more points are likely to have smaller distances to 0, 0 than say a point 2, 0, which is farther away than the center because of the shape of the distribution. Of course, if you are looking at a bivariate normal distribution that's centered at 2, 0, you'll see a different pattern. But just because we are taking this shape, it looks that way. Okay, so coming back to the question, can distance profiles characterize P? So by very classical results, Borel measures are uniquely identified by their values on a Borel algebra, which is generated by closed balls. Now, Borel algebra means you have all the finite unions, intersections, complements, and so on. But what we are looking at here are just the distance profiles, which are just their values on closed balls. And we know that if we are in the Euclidean space, then a measure is completely identified by its value on all possible closed balls. But is this true if we go beyond Euclidean spaces? What happens in general metric spaces? Can the collection of distance profiles evaluated at all centers and all radius identify the underlying distribution? The answer in general is no. It does not hold for all spaces and all distributions. But luckily, it does hold for a broad class of spaces and a broad class of distributions. So I'm just going to present two situations where this will hold. So the first situation that I'm going to talk about is a condition on the measures, which is referred to as the doubling condition. So a probability measure mu is said to satisfy the doubling condition if its rate of growth for very small radius is uniformly upper bounded by a constant. So the value of mu at a ball of radius 2r divided by its value on a ball of radius r. So that's like how fast the measure grows on balls. that is uniformly upper bounded by L mu, and we need it only for R goes to 0. So this is a very mild condition, and as long as the underlying measures satisfy this condition, then the measures will agree, as long as they agree on all closed balls centered at the support of either distribution. And that one is going to be important later. We don't need it for all the points in your space. It's enough to just have them agree on balls centered in the support of one of the distributions. And this is a more common condition that comes up with other approaches working on metric spaces. So suppose this is a condition on the space, irrespective of the measure. So suppose omega d is a space of negative type. Negative type means that the metric satisfies this condition, that as long as you have finitely many xi's, and you can get this property as long as alpha is sum up to 0. And this is a very easy condition. Most spaces will satisfy this. And omega d is of strong negative type if, in addition to being of negative type, this map, which is called potential, the potential of the measure mu, is injective on the class of measures. So just to say which spaces, again I'm back to that. I'm not sure what I'm doing, but I'm very sorry that this is happening so frequently. Okay. So Euclidean spaces, separable Hilbert spaces, hyperbolic spaces, spheres with at most one antipodal point, all of these spaces are actually of strong negative type. So it's quite common to come across strong negative type spaces. In fact, it's harder to come up with spaces that are not of strong negative type. But even in such situations, as long as the metric D is such that D power U is of strong negative type for some U, we have that the class of distance profiles will completely identify the measure. So in a nutshell, what this slide is intending to do is saying that for all the other methods which comprise of the state of the art that work with the strong negative type assumptions, the distance profiles will still do their job. They will still be able to characterize measures using just the distance profiles. So in the last few minutes, I just said that there are two situations, doubling condition on the measures or strong negative type conditions on the spaces, and together they will help the distance profiles totally characterize your underlying measure. Now, just a digression from the actual independence testing problem. Because distance profiles can be used to characterize measure, one very immediate thing is they can be used for two-sample testing. So a classical two-sample test is of this form, where you have U1 to UN coming from a distribution P1 and V1 to Vm coming from another distribution P2, where you want to test that P1 is equal to P2 versus P1 is not equal to P2. And I will again motivate the problem with a toy example. Here we have two distributions. This is the standard normal distribution and the t distribution with 8 degrees of freedom. And if you look at this highlighted point, I have plotted its in-sample distance profile versus its out-of-sample distance profile in the right plot. So the blue curve here is its distance profile with respect to only the orange points, because the highlighted point is in the orange group. And the out-of-sample distance profile is its distance profile with respect to the blue points. And you can see that for this one single point, these are two very distinct curves. And you can get these two distinct curves for every data point in your sample. And that's what we will use for constructing the two-sample test. So the idea is that for every point, Ui and Vj, you will look at the difference between their in-sample and out-of-sample distance profiles and just aggregate that information. So here TNMR is just the aggregated difference between these, like the difference between the in-sample distance profile of UI versus its out-of-sample distance profile, and similarly for Vj. And then you can have this whole stochastic process giving you an idea of how different the two populations are, and you can aggregate the information either by taking an integral of this whole statistic or by just taking its maximum value. And I'm not going to get into the details of this, but you can check our paper that recently got published if you're interested in this test. Okay, going back to the independence testing problem, the answer is 3. So in 3, the random distributions are actually dependent on the random networks, and in 1 and 2, they were independent. So that's exactly what we are going to do for the rest of today's talk, where I'll provide a way to give you a p-value for doing this problem. Okay, just to set up some notations. Here we have multivariate random objects. So say you have p different random objects which could belong to p potentially different spaces, omega 1 d1 to omega p dp. In the previous example, say omega 1 was the space of networks, and omega 2 was the space of distributions. And then one could have other things that one wants to put in the same testing problem, like in case you have other objects, like which is not quite uncommon if you have those multi-omics data and so on. And this P here is the joint law of all these P random objects. And if we equip the space with this maximum metric, then one can actually create the Borel sigma algebra of the product space by using the product of the Borel sigma algebras of the individual spaces. So this is just giving some regularity conditions to prove theorems and so on. Important thing is P is the joint law, and then one could also define the product law, which is the product of the marginal laws of these random objects. So the classical independence testing problem is you want to test the null hypothesis that the joint law is equal to the product law versus alternative that they are not equal. So in order to do that, I'm going to use something called the joint distance profiles. Now, what is a joint distance profile? It is the joint distribution of the distances at p different centers. So small x1 to small xp are the different possible centers in the p different metric spaces. And then you're looking at the joint distribution of distances around these p potential centers. Is it clear? It's yeah.
Have to choose those small x's, or do you have some guidance on how to choose them?
That's a great question. Let me hold on to that for a couple of minutes. Yeah, so the centers are very important. So basically, these joint distance profiles are the masses of the joint law on the products of these marginal closed balls. Now, one can characterize independence using these joint distance profiles. Suppose that both your joint law and the product law satisfy the doubling condition that I mentioned at the start of this talk. So independence, which is the equality of the joint and the product law, is characterized completely by the equality of these joint distance profiles and the product of the marginal distance profiles for every point in the support of your joint law and for every possible radius. So there is an answer to your question that in order to characterize independence, we need the equality of the joint distance profiles for all points, like the centers, which are in the support of the joint law. You need not look further. You can just look at the support of the joint law and evaluate your distance profiles on those, the joint distance profiles and the product of the marginals, and get your independence characterization. And this also very naturally gives us the idea for constructing the independence test. What I would do after I learned this is I will compare the joint distance profiles with the product of the marginal profiles for every x in the support of the joint law and for every radius. Now, of course, this is not free. We have to be able to estimate these quantities. So, simple plug-in estimates will work. We have samples generated by the joint law, right? Like that's what we have to start with. So what we will do is we'll use those samples to construct the joint distance profile. Very usual way to estimate CDFs, joint CDF here. And then we'll also look at the product distance profiles, which are just one-dimensional in each space. And then we will use these plug-in estimates of the joint profile and the marginal profiles for every point in your data. So those will be our centers. So basically, we'll look at x1 to xn, which are p-variate random objects. And then those are going to serve as your centers for creating the joint distance profile and the marginal profiles. And then in order to create the test statistic, we'll just compare these bunch of joint and marginal profiles for every data point in your sample. So here's the test statistic. In order to define the test statistic, I'll have to introduce what are WX. So WX are data adaptive weights that we want to put on each point. And these WX are a function of not only your point, but also the radius. So in order to compare these joint and marginal profiles, we are also going to say that, okay, we want to put that much weight on point xi, and then we are going to also put that much weight on the radii. So there are two versions of the test statistic. One is when one can actually look at the difference between the joint and the marginal profiles, in fact, the weighted difference, and integrate them across all possible radii, but according to the joint law. But one could also do that using the product law. So I'm not going into too many details of how the product law could be better in some situations. I'll show them later in the simulations. But in fact, even in a few slides, I'll show you connections between this and the Hoeffding's test. And even there are literature where it has been shown that even for Hoeffding's test of independence, it could be better to take the integration over the product law instead of the joint law if you want to characterize all kinds of independence. So I'll discuss this later. But we are not the first to, how we created this is we first tried to look at this test to look at the difference between these joint and marginal profiles. But later we found that some special cases of this actually exist in the literature. So when we have trivial weight profiles, this test statistic actually corresponds to the Ball covariance. And when we have Anderson-Darling-like weights, this corresponds to the HHG test. So both have been explored previously in Euclidean cases. But what we are going to do is we are going to take this whole class of test statistic and try to be very general and make them applicable to general metric spaces. Okay, I'll take a moment here. Is the statistic clear? Yeah.
Line on this doubling condition.
Yeah.
Is that easy to check? Like, do you get it from the context, or there are ways to check it?
That's a good question. So of course it can, because we are trying to be very general, if you have a very weird space, you may have to check that. But for all the examples, as you will see, they hold very generally, like it's a very mild condition actually. Okay. So just a connection of this test statistic with Hoeffding's test. So when you have p-variate random objects, you actually have, if you look at each coordinate, you have p possible distance matrices, right? Like, let's call D1 to be the distance matrix of the first one, D2 the distance matrix of the second one, and until dp. If you extract the ith row of each of these distance matrices, that ith row will give you the distance of every point from the ith data point, right? And that is enough to look at the distribution of distances around the ith point. So how one can imagine this is that one extracts the ith row of each of these distance matrices, and using these ith row, one can get p different columns of distances from the p different possible objects. And what you have, so this is just one illustration with a specific with specific weights to be 1. What you see as the summed here is actually the BKR test of joint independence of the distances in the ith row of every distance matrix. So this is in fact equivalent to the Hoeffding's test plus 1 over 36. So that's very weird, but it's just how Hoeffding defined it. He had this very peculiar 1 over 36 coming up, but they are doing the same thing. So this BKR test evaluated on the distances of the ith data point to everybody is what you have in the inside, and then you sum this for every data point to get the test. So here what we are doing is we are just applying the Hoeffding's test to the different distances for every data point and then aggregating over all the possible data points with different weights. Okay, just a visual break because we have a few intensive slides coming up. Just in case you have any questions, I'd like to take them at this point.
What is this step taken from?
Oh, this is actually my favorite hike when I was a student at Davis. It's at the top of the Pyramid Peak in Desolation Wilderness. So it's like some wilderness area near Lake Tahoe. Okay, 10 minutes. Okay, so I'll need to really be fast here. Okay, so I'll be very quick on the theoretical result. Just the key challenges, these are not very easy to deal with theoretically because you're estimating the profiles using the same data as you are using to create the test and so on. So there are heavy dependencies. So one needs to really sit down and cancel all these dependencies. And you need some kind of uniform convergence of these joint distance profiles, which will help us get the limit theorems for the test statistic under the null and to prove its consistency under the alternative. So just this is the very key result that's coming up in the theorems later, that the joint distance profiles are on target and they converge to a zero mean Gaussian process with a certain covariance. I'm not going to go in depth into that. but it needs an assumption. So this assumption is an assumption on the complexity of your space and on the joint law. What we need is this class of indicator functions to have finite L1 bracketing number. Not only finite, it needs to have this rate. Again, this is very mild. Actually, if you all of our examples fit into this situation, and an easier way to visualize this assumption is if the joint profiles are uniformly Lipschitz and each metric space has covering numbers growing in this fashion, then that assumption is guaranteed. So these are easier to verify because it's easier to just know the covering number of a metric space. However, that assumption is more mild. Like these could require you to have continuous joint distance profiles and so on, but we don't need it. It actually applies also to discrete cases. So how does the distribution of this statistic look like under the null? So together with that assumption and the assumption that the weights that we are taking in are uniformly consistent, both the joint and the product versions of the test statistic converge asymptotically to the law of an infinite mixture of chi-squares, where the mixture weights are the eigenvalues of a particular covariance that we figured out explicitly, but it's too long to put here and not important. So just know that they are the eigenvalues of a certain covariance that one can estimate asymptotically. And also, one very interesting property that was not discovered before is that if you have the trivial weight profiles, then this test is actually asymptotically distribution free. So this is a good result because here it means that these lambda j's, which are the eigenvalues of the covariance operator that we defined in the previous page, no longer depend on the data points. And for when p is 2, these are actually the eigenvalues of a product of a Brownian bridge, basically. So these are actually the same distribution as the classical Hoeffding's test when you have trivial weight profiles. But when the weight profiles are not trivial, then these are actually data dependent. So in sticking with tradition, like if we know these quantiles, or we are in the distribution free case, or we have a large sample, we can actually try to just approximate these. So we can approximate these quantiles from just by knowing the CDF. But typically, if you have non-trivial weight profiles, then this one is data dependent. And in that case, it may not be easy to get these quantiles. So we use the permutations. We use permutations to approximate these quantiles. And permutation is very simple. Just imagine you're permuting x and y independently and just looking at the, you compute the test statistic again and again by permuting the x and the y independently and just get the p-values that way. One more small result before we move on to the simulation is that one can also get guarantees of power under alternatives that are very close to the null. So these are the population targets of our test statistic. And these characterize independence under very mild situations, as we have seen before. So we are considering alternatives of the form when these quantities are going to zero. That is, they are shrinking to the null, but not at a very fast rate. Like n times this one goes to infinity. And as long as you have this kind of a departure from the null, both our asymptotic and the permutation tests are guaranteed to have full power as n goes to infinity. Of course, these are all large sample results. Okay, so I think I may have, 2 minutes? Like, okay. So again, I think I will skip this picture and show you some simulations. Again, it's very routine way how we did the simulations. We are calculating the proportion of rejections out of 200 Monte Carlo runs. We take n equal to 100, and wherever applicable, we take dimension to be 20 and 40. And we use 500 permutations to evaluate the cutoffs. And the methods we compare against are the gold standards, like the very famous distance covariance, which characterizes independence using only distances, and the d variable HSIC, which is also very popular in the kernel learning literature. Both of these are actually related, but they are actually the methods that one will apply as long as one has distances. So again, in order to create these simulation settings, I'm going to simulate some underlying distribution from a Gaussian copula, which has sigma to be its covariance matrix that controls the dependency structure, and F1 to Fp are the marginals, where you can control how the marginals are, and you can control the dependency structure using sigma. And then we are going to have this rho dictate how much of the variables are correlated with each other. So in many situations, rho equal to 0 will characterize independence, and then as you move away from 0, it says that the underlying variables or objects are more and more dependent. So here is a very hard example from independence testing point of view, which is just taking normal random variables and looking at their sign and cos. And here we see most of the methods cannot have power except for the product versions of our test and the DHSIC.
What scale is
L is the dimension, just how the dimension of the objects, basically. Okay, so I think I may not be having too much time, so I'll just jump to the non-Euclidean examples. So we have tried this for a variety of situations in Euclidean cases, and it particularly has very good power for heavy-tailed situations. When you have outliers in the data, this is very hard to break down. And then we have various kind of dependencies arising out of support restrictions. Like if this and that happens, then your data is this way, or if that and this happens, then this is that way. Then in those situations, we have very good power compared to the distance covariance and DHSIC. Now here are more complicated situations. Okay, so these are random networks paired with random vectors, where we generate the data according to some copula, and then we split the data into two parts. We take the second part to be our Euclidean part, and using the first part, what we do is we generate a complicated function that gives rise to a random network that follows the preferential attachment model. So how preferential attachment model works is you start with a node and then you keep adding nodes to the network where the attachment function is proportional to degree power gamma I. And then we let this gamma I be random and depend on the first half of your data. And in this situation, you can see that the new methods perform much better than existing counterparts. And also particularly the product version of the test is quite powerful. Here we have a random network coupled with random networks, where again, we try to make it as complicated as possible. We have stochastic block models whose community building probabilities are correlated with each other. Okay, in some sense, that's how we create these paired random networks. And then 0 means independence, and as you go far away from 0, it's getting more and more dependent. And the new methods are actually particularly powerful as compared to distance covariance and DHSIC. We have random distributions coupled with random vectors and random compositions coupled with random vectors, but I think I will I don't have time, right?
2 more minutes.
Okay, then in the last 2 minutes, I'm going to just show a data example. Here, we are trying to see if the hourly bike compositions are independent of daily temperature distributions, humidity distributions, and wind speed distributions. And for this, we are using a bike sharing data collected in Seoul in the year 2018. And here are the p-values that we got out of permutations using the different methods. And we split the analysis into different seasons because, of course, different seasons are different. We didn't want to have any confounding due to the seasons. And we have 3 different predictors. Like, these are important because you might be wanting to predict compositions using these distributions. And does such a model make sense? Because if they are independent, you would not bother. You would not bother to make such a model. So here we correct for multiple comparison across the seasons and for all the testing that we are doing. So we have actually 12 possible comparisons, and we are doing something very simple, just doing Bonferroni correction to the p-values. So we highlight the p-values that are significant even after doing Bonferroni correction. And you can see that the new methods are more powerful to detect the dependencies as compared to the existing methods.
Real combinations. So what are they? So basically, this is testing of independence, right? And you are trying to say, like, test whether this temperature, humidity, wind speed, like, they depend on each other or independent. And where do, like, so many tests come from?
Oh, because we have 4 seasons.
Okay.
So we did the test separately for each season. And then we have 3 different predictors like temperature, humidity, and wind speed. So 4 cross 3.
So that can be 4 tests. And now.
No, 4 tests for each predictor
Oh, I see.
because we have 3 of them. So we have 12 tests that we are doing simultaneously.
But so you are testing it like temperature independent with humidity, or you are kind of testing like 3 of them together, like
Together. Yeah. Yeah, this can be done in a more sophisticated way, I'm sure, but this is just Bonferroni correction. Yeah. Okay, so just quickly summarizing, what all checks out is that we are providing a test that has type 1 error control, and even under alternatives that are very close to the null, and using the permutation p-values. So we have worked out all those guarantees, and we discovered that these are distribution free for trivial weight profiles. We do not need tuning parameters, like the DHSIC is reliant on a kernel and the kernel bandwidth, and at least in my experience, when I tried to make them work in the simulation, it's like a game of hunting out the what will work versus what won't. So of course there are some heuristics, but there is really no way to know that this is the best kernel with the best like bandwidth. And we do not need sample splitting, so we can get the explicit asymptotic distribution even with all these dependencies. And hopefully I've convinced you to some extent that this can be promising empirically. So yes, that's all for my talk today, and some future directions. It'll be interesting to see what are the high dimensional behavior of these statistics, because at this point we only have empirical evidence. We do not know how these will behave if your dimension also goes to infinity. And a very immediate consequence is, can one design conditional independence testing for random objects? Again, also this could, another immediate consequence is, can one test serial independence in object time series? So these are all like exciting things that are coming up. And I want to thank my collaborator, Yaching Chen at Rutgers University, who was my collaborator on this project. And thank you for your attention.